I was about to just write in a bunch of work. We're going to practice these problems in my class tomorrow, and I figured my students would like to, at least some of them, hear my thought process on using these inverse trigonometric derivatives. So as it says here, you're going to need to know more than just those inverse trigonometric derivatives. So like maybe the derivative of trigonometric functions, chain rule, product rule, quotient rule, things like that. When I see inverse cosine of 2x cubed, working from the outside in, I now have to deal with the derivative of inverse cosine first. So I don't really think of the derivative of inverse cosine as -1 over the square root of 1 minus x squared. I think of it as -1 over the square root of 1 minus the input squared. And once I write in, hey, the input to the inverse cosine, that input in the denominator, I missed my squared, that input is 2x cubed. I know I have to use the chain rule, so times the rate of change, 6x squared. I guess I could rearrange. I don't have to, but I might as well. So that derivative is going to be, bring that negative 6x squared into the numerator. The square root of 1 minus 2 squared is 4, and x cubed squared is x to the power 6. So very similar problem. The derivative of inverse cosine, no matter what, is going to be -1 over the square root of 1 minus that input squared. In this case, the input is cosine, and since that input is not plain old sine, I know I need to use the chain rule, and multiply by the derivative of cosine, namely sine of x. So we'll go ahead and rewrite. dy dx is -1 times negative sine is positive sine of x in the numerator, and square root of 1 minus, I guess I'll write cosine squared x. That's the best way to go in the denominator. You know, repeated reasoning always helps. So again, we're using inverse cosine as this outermost function we have to deal with first. And the derivative of inverse cosine is -1 over the square root of 1 minus the input squared. What input? Oh yeah, tangent. That's not a plain old x. So we need to use the chain rule multiplied by secant squared x, the derivative of tangent. Let's go ahead and clean up. So dy dx is negative secant squared x over the square root of 1 minus tangent squared x. I think that's good. Ooh, finally a different inverse trigonometric function. We're still not going to really care what's inside that inverse tangent, at least at first, because the derivative of inverse tangent is 1 over once the input squared all in the denominator. What's that input? Oh yeah, something else. 3 minus 5x, which has a rate of change of, I'll just write it this way, 0 minus 5. You don't really need the 0, but yeah, whatever, maybe just -5. So y prime is going to be -5 over, oh man, algebra stinks. So 1 plus, and maybe I'll do that with parentheses, 9 minus 30x plus 25x squared. And one more, -5 over, maybe I like a different order, 25x squared minus 30x plus 10. Ooh, the equation of the tangent line. So my answer is not going to be dy dx is equal to some number, right? That's just going to be the slope of the tangent line. I'm already thinking my answer is going to be y minus some y value is equal to the slope, which I'm going to find using the derivative of inverse secant at 2. and then x minus the x value, which I actually already know is 2. That's my whole plan. So let's see. Oh, inverse secant. I've memorized that derivative. Let's see. Y prime is 1 over the absolute value of x, square root of x squared minus 1. And let's see. We're using x equals 2. And y prime is 1 over, I don't need absolute value there, and 4 minus 1. And so what do we get? 1 over 2 root 3. And you can leave it that way, but I don't know. I think a lot of people are taught, hey, rationalize, so root 3 over 6. Multiply by square root of 3 over square root of 3. All right, that is not the equation of the tangent line. Oh, man. That's a bummer. I need a y value. What am I going to do to get that y value? Well, let's go back. So y is equal to inverse secant of 2. And, inverse secant of 2 has something to do with cosine of 1/2. And the domain or restriction, or however you say that, for cosine and for secant are the same. I'm expecting a first quadrant value, so it turns out that's y is equal to pi thirds. Probably not a great explanation if you don't already agree. So I guess what I'm thinking is in the first quadrant of the unit circle, this angle, pi thirds, has an x value of 1/2. Or you guys are kind of taught this way, right? 1/2 for the x value, root 3 over 2 for the y value. So cosine of pi thirds is 1/2. That's almost the same, but not identical to inverse cosine of 1/2 is pi thirds. And I guess what I was thinking is inverse secant of that reciprocal 2 over 1 is also pi thirds. That's maybe a better way to go. All right, but let's just get rid of that because ideally you know trigonometry. So we need to switch gears and say, hey, we're writing a tangent line. So tangent line to inverse secant of x at 2 is going to be y minus pi thirds is equal to, what's the slope? Square root of 3 over 6. Actually, I don't like that. I like 1 over 2 root 3 times the quantity x minus 2. Ooh, fun. The derivative of this thing with respect to x, I can already see. Well, you kind of have to look for structures. And the structure I see is y is actually some function times some other function, right? That's what's going on overall. So I'm going to have to start off with how to find the derivative of a product of two functions. And the derivative of a product of two functions is the first function times the derivative of the second function. I feel like that's going to take me a while. I'll come back. Plus the second function times the derivative of the first function. Okay. So I need to put in my derivative of inverse sine, and the derivative of inverse sine is 1 over the square root of 1 minus the input squared, and that input is 2x, which has a rate of change of 2. That's kind of ugly. I'm not going to do a ton of rewriting. I'll do a little bit. So y prime is 2x squared over the square root of 1 minus 4x squared. And that other side is going to pretty much stay the same. I'm going to write my 2x out front, then the inverse sine of 2x, just to make sure nothing got rearranged. Or, hey, this 2x has not anything to do with the input of inverse sine. The last problem overall was a quotient of two functions. This function is really, well, I said quotient, huh? That was a product of two functions. This is a quotient of two functions. And what? The derivative of a quotient of two functions is the denominator, got that, times the derivative of the numerator. I'm going to put my negative out front. The derivative sign is negative, cosine is negative sine of 3x, which has a rate of change of 3, okay, minus the numerator, cosine, times the derivative of the denominator. I feel like I'm going to get lost, but I'm going to keep going. So let's see, that's my new part. The derivative of inverse cosine is 1 over the square root of 1 minus the input squared, and that input is 2x, which has a rate of change of 2. Oh, that was it? All right. That wasn't bad. And then continuing on with the quotient rule, let's see. The denominator times the derivative of the numerator minus the numerator times the derivative of the denominator all over the denominator. Square. Oof, that's really ugly. I am not going to simplify that or rearrange, but really quickly, something I know I should mention that I often see stressed out students do is try to divide out one of those inverse cosine of 2x's in the denominator. You, of course, can't do that. The numerator is a subtraction. You have to get rid of that subtraction first. Ooh, should be easier, but yay, implicit differentiation. So the outermost function here is the inverse tangent, or at least on the right-hand side. So when we take the derivative of y, that's dy dx, or if you like, 1 dy dx. The derivative of inverse tangent is 1 over 1 plus the input squared. That input is x times y, which is a product of two functions, and the derivative of a product of two functions is the first function times the derivative of the second function plus the second function times the derivative of the first. Well, that's sort of a bummer. Let's make that an x. I should collect my dy dx's, but then I look back and maybe past me was pretty smart and I said, hey, differentiate. I didn't say find dy dx, so I think I'm okay. I hope you have the algebra skills.